I'm Caraballo. I work for Fertiberia, and I'm going to present the title of my presentation is Novel Molten Salts as Thermal Energy Storage Materials and Heat Transfer Fluids. We are a part of the Empower team, and we have developed several new fluids to be used as TS materials and also as HTF. Okay, first of all, I'm going to introduce my company. Grupo Fertiberia is an industrial company with 14 production sites. We produce mainly fertilizers, also industrial solutions, explosives, and other chemicals. Our production capacity is about 5.5 million tons. Our market share is in Spain and Portugal is more than 75%. Also, we have facilities in France, and we sell all over the world. We are more than 1,400 employees, and as I said before, our main the core business is fertilizers and nitrates, mainly nitrates. About this, I'm going to present the production facility that is more related with this project. Quimica Estroncio is located in south of Spain, in Cartagena, in the Mediterranean Sea. This is a multi-product factory that can produce more than 50,000 metric tons per year. And we can produce any kind of nitrates, from calcium nitrate to potassium nitrate, ammonium nitrate, etc., and all type of grades. One of our star products it's for microelectronics, and it's more than 3 nines purity. So we are able to produce very fine chemicals also in a industrial scale. So it's a nice and interesting facility. And the reason I'm presenting this is because 2 out of the 4 TS material components were produced in this factory. Okay, Fertiberia's role in Empower is the high thermal capacity materials for thermal storage work package leader. We work along with CA and Enea, and testing and validation work package partner that was led by Enea. In this work package, there were 3 main objectives: the selection of high thermal capacity and robust TS materials, so to speak, the development of new TS materials apart from the all-known solar salt or other compositions that are commercial and all we know have several drawbacks. Also, the empirical validation of TS materials under simulated conditions, achieving TRL 6, that was foreseen to be done in Enea. And this TS material simulated in different TS systems, thermocline and multi-tank, that were developed by CA. To show the reduction in the TS system and allowing a final reduction of about 20% in CAPEX. As you know that the thermal energy storage system is one of the most expensive parts of a CSP plant. As I look at the participants in this workshop, I think everyone knows this concept. Every of you know the thermal energy storage, along with the solar field and the power block are the main parts of a CSP plant. Also, these materials is the basic component in the thermal energy storage that store the energy that is from the solar field in a direct or indirect mean. Let's say if there exists a heat transfer fluid that transports the energy to the thermal energy storage. Okay, I will go. We can review briefly the state-of-the-art materials. As you know, the main TES material is solar salt that is a non-eutectic composition and with a fusion temperature of 240 degrees, and the operational range is about 280 to 380 degrees. In the case of indirect system, or in the direct up to 565 degrees. On the other hand, HTF materials, thermal oils that are based on diphenyl ether and biphenyl mixtures. The main, I think, we all know the terminal materials that is, I think, are the most used materials in this field. That one of their main drawbacks are their temperature stability lower than 400 degrees, and that they are toxic and non-environmental friendly. So there are different objectives and different ways to enhance the performance of these materials, and here you can see some of them listed. The increase in the temperature range, it's very interesting because as long as you keep increasing the temperature range, the efficiency of the power block increases also. So an ideal material can be one that can operate from about 100 degrees to 600 degrees. Also, the physical-chemical properties enhancement is another field to improve these materials, mainly in terms of specific heat capacity by let's say different compositions of the material, or also by the addition of nanoparticles and making nanofluids. That it has been demonstrated that it can be a new way to enhance this property. Also, density is another property, probably less known, but very important, because along with the CP gives you the energy density. So it's of main interest to increase this indicator. So it's also very interesting to have a high density material if possible. Also, another way that is related with the first enhancement of the object is the temperature stability. As all you know, all the nitrates lack of stability at about 570 degrees or something like that, with the composition of nitrates into nitrates and another compounds. So if we still want to work with nitrates, we need to try to see if under other atmospheric conditions, let's say nitrogen atmospheres or other atmospheres, this decomposition can be avoided, or the temperature decomposition increased, or just to avoid these components and try to develop other nature materials with this without this low temperature stability, like fluorides or chlorides or carbonates or whatever. Also, the reduction of stock of the TES material is also a very important thing, because as you know, the CAPEX of a CSP plant suffers a lot of this matter, because it represents about 20 to 25% of total CAPEX. So if we can reduce a bit the stock of this material, it's directly a reduction cost of the CSP material. Also, with thermocline tank systems, it can be also reduced by means of you have only one tank, not two tanks. So that's another CAPEX reduction. And to finish this slide, you have also the efficiency enhancement by coupling thermal energy storage and HTF, and to promote direct system over indirect systems. Okay. Starting with the selection of and optimization of these materials, we have to work with the CALPHAD method. It's a thermodynamical method that uses experimental information, empirical rules, and fundamental theory to model thermodynamic properties of each phase of the system. In our case, we worked with four components, 4 nitrates, and four different phases: liquid phases and other solid phases. So we modeled the Gibbs energy of these phases with model parameters that are available in different thermodynamical software. And we predict the behavior and the phase diagrams of all these components. Let's say 6 binary diagrams, 4 ternary diagrams, and 1 quaternary diagram. To detect the best composition, we were always looking for the euthetic composition, that is given any mixture of n components, the euthetic composition is the minimum temperature composition of all the systems. So and it also behaves as a pure component. It's not like solar salt that, as you know, it starts melting, but part of it remains solid. So an euthetic composition will at melting temperature will all became solid. So this is also useful in terms of local low temperatures that don't unplug the system due to local solidifications, and it seems to be a good approach. This, as I said, we developed this model for a 4-system material component based in alkaline and alkaline earth nitrate based. Mainly, we start our work with solar salt, and we start adding other components and seeing if we can enhance the molten temperature and also other parameters. We used thermocalc and FactSage software and databases, and we successfully developed, as I said, all the system, and we could assess all the phase diagrams that are part of the system. Here in this slide, you can see the well-known sodium potassium nitrate phase diagram, and in the right you can see the one of the ternary diagrams with strontium nitrate. That was one of the other materials of the quaternary system. And in this case, for example, this ternary diagram, the eutectic composition was about 210 degrees, the melting temperature. This assessment, this thermodynamic assessment, cannot be done without experimental studies. mainly differential thermal analysis and X-ray diffraction studies to determine the diagram phase shape and the minimum temperature compositions. The endothermic peaks of the DTA gives you the information of what is the liquidus or the solidus of a given composition, and on the other hand, the XRD graphs can give you also the present phases in the solid state. So in terms of modelization, this can be used to tune the model developed in CALPHAD, and to also and to give the more robust model, and to give the good results in the final case. Other thermophysical properties, so to speak, CP, density, viscosity, and thermal conductivity were determined by experimental means. Also, talking about corrosion studies, the addition of new components to the system can be tricky, because these new components can be more corrosive or hard to the conventional materials used in this technology. So we test about 2,000 hours with one of the compositions at 4 to 5 degrees, and almost 5,500 hours with the other composition at high temperature, to test 6 different conventional steels. For example, AC 304, 316, 316 with titanium, 321, and so on. And we develop also CMC studies, oxide layer behavior, we determine weight loss, and EDX studies, all well carried out. And the results that for those temperatures that are let's say the more aggressive conditions for the two salts, similar results were obtained than for solar salts. So we expect the same corrosion behavior in any conventional steel that for the solar salt dot. So one of them of the problems were avoided. We can use these compositions without problem in conventional stainless steels. Okay, in this slide I present the result and the comparison between solar salt and the two salts that were developed in this project. In the first salt, as you can see, enhance the melting temperature about 130 degrees to the solar salt one, while the other one only 20 degrees. The decomposition point, however, in the first salt is about 100 degrees lower, but it seems to be useful, this composition for low temperature applications. Also, you can see that the density is in the range of plus minus 10% to the source salt. Also, the specific capacity, thermal conductivity is almost the same. As you know, it's no big change in these materials. And also the viscosity, it's similar. It's true that for salt one at low temperatures is greater, but it remains in the same ranges as high tech, for example. So we're talking about a composition that can substitute high tech. So it's a good candidate. And finally, in terms of CAPEX, the first salt, it's true that it's more expensive, but in the same rates as high tech. And on the other hand, the other salt is about 10% cheaper. So in the future, it can be it can be another candidate to substitute the solar salt. So finally, to compare in a graphical way, you can see the temperature range in a indirect system with solar salt and oil. Then in a direct system with solar salt and with salt as also a direct system, we can increase a bit the gap. And in case of the other salt, we can see that we can reach very low temperatures and with only decreasing the high temperature about 100 degrees. So for certain applications, this salt can be studied and can be considered to be installed. And okay, this is all. We can sum up all this work in a few sentences. We have developed two high thermal capacity and robust TS materials. We proved that CALPHAD methodology and DTA extra-day studies is the best way to develop new materials. It can be used without a lot of cost and time, and you can make many things in the best way. Also, the enhancement of CAPEX was achieved, and along with the operational temperature ranges and thermophysical properties. Also, the corrosion behavior is similar to standard TS materials, so there is no need to install different materials for this application. So it has we have here the potential to substitute directly the solar salt for one of the other compositions developed here and keep working without any problems. So thank you for your attention, and that's all.